let us discuss the simulative test in detail. So, I will be discussing the dry wheel tracker test in this lecture. So, there are various test protocols for a simulative test or a dry wheel tracker test. One is the AASHTO protocol, which is AASHTO T324, which uses a Hamburg wheel tracker for the testing, wherein the rutting as well as the moisture susceptibility of the material can be determined. So, you can do the testing in the dry condition as well as in the wet condition. Now, the specimens for this testing are either cast using Superpave gyratory compactor, or you can have field cores also that are taken from the field, or you can have so-cut slab specimens also can be used in this test as per this test procedure. And the next is the European standards EN 12697, which suggests the use of large size, extra large size and small size devices, wherein the rutting susceptibility of materials with aggregate size less than 32 mm can be determined. Again, the test can be conducted in air or water. Now, in both these tests, how they differ is the way in which the load is applied or the sample preparation and things like that. In both the tests, what is done is that the sample is prepared in a fixed mold, as you can see here. So, this is a steel mold in which the sample is cast, either a slab or a cylindrical specimen, and then the wheel load travels on top of it. Now, the major problem with this is that this the mold that is there, which offers a very rigid confinement to the material. So, even if the material tried to flow, it will not be able to do so, since the edges are fixed in nature. Now, this aspect is considered in the ASTM studies, and they are trying to refine the code with considering this aspect as well, to have a mold which does not offer a very rigid confinement, or which offer a confinement which is as prevailing in the field condition. But this ASTM standard is only a working standard, the draft only is available. So, I will not be discussing this standard in this lecture. So, let us discuss the European standard. So, I will be discussing the rut wheel testing using the European standards. So, I will read from the code. It says that the susceptibility of bituminous materials to deform is assessed by the rut formed by repeated passes of a loaded wheel at a constant temperature. So, this is what is done in this test. As I said, you can have three specimen sizes. One is an extra large device, next is a large size device, and then is a small size device. Okay. So, in the extra large size device, the specimen is a rectangular in shape with 500 by 700 mm, and the thickness, if specified, is 60 mm. Otherwise, you can have it at different thicknesses of say 30, 40, 50, 100, etc. based on what is the thickness in which you are going to lay the material in the field. Okay. And in the large size device also, the specimen size is of rectangular in shape with a specimen size of 500 by 180 mm, and the thickness, as I said, can be 50 mm if your layer thickness is going to be 50 or less in the field, or you can have a 100 mm thick specimen if you are going to lay the layer with more than 50 mm in the field. Then you have the small size devices with 260 by 300 mm. Rectangular specimens, or you can have 200 mm core specimens also. Again, the thickness is decided based on the nominal maximum aggregate size of the mixture. If see, your specimen size should be at least 2.5 times more than the upper sieve size of the material. So, this is a classification or comparison of the different devices, the extra large size, the large size and the small size device. The loading in each cases, in the case of an extra large size device, you go for a loading of 10,000 Newton plus or minus 100 Newton, but the pressure applied through the wheel load is 600 kPa. Whereas in the case of a large size device, your loading is 5000 Newton, and in the small size device it is 700 Newton, whereas the pressure remains the same of 600 kPa. Now, the loading wheel in the case of an extra large is as well as large size device is a wheel with pneumatic tires without any tread. Okay. Whereas in the case of a small size device, you use a treadless tire with a solid rubber outer covering. Then the track width, when I say track width, it is the width of the wheel which passes on top of the surface. The track width for extra large size is 110 mm, whereas for large is 80 and for small size device it is 50 mm. Okay. And the frequency of application of the load, that is frequency, when I say frequency, it is the onward and the return moment. So, these together, the forward to backward moment comprises one cycle, and the frequency of cycle is 2.5 Hertz if it is an extra large size device and 1 Hertz for a large size device, whereas in the small size device it is 26.5 load cycles per minute is the frequency that has to be provided. Now, the specimen, you can have the specimen being prepared in the specified mold for the testing. You can use any compactor to compact the specimen to the required air void content. We normally do the testing at a 4% air void. So, at this air void, you can cast the specimen in the mold itself, or you can cast the specimen using any other compactor. So, you can use a shear compactor to prepare the slab specimens, and if the size of the sample is less than the mold, you have to fill in the extra spaces using plaster of Paris so that it fit properly inside the mold. Okay. Now, if it is a core specimen, see, you want to study the rutting of the material in the field, you take a core from the field and you have to ensure that the specimen is placed in the mold so that the direction of field load application is same as the direction of the traffic in the field. And you should have more number of specimens to check the repeatability. In the case of extra large size device and the small size device, you need at least 2 specimens to check the repeatability, whereas in the case of there is a small size device of type A in air, it requires at least 6 specimens to be used. And how this data is collected or how the deformation is measured on the surface of the specimen. So, you have a specimen and a wheel traverses on the top of the specimen. In the case of an extra large size device, the profile of that surface is measured using lasers. Now, suppose this is a specimen. At 3 different locations, you will have the lasers. So, this is the direction of movement of the wheel. So, at 3 locations, you collect the profile of the surface. Initially, you take the initial profile, and then after regular intervals of test cycles, you take this profile using the laser at 3 different locations, so that you can get the entire top cross section at 3 locations. Okay. Whereas, in the case of large size device, the measurements are made either using an LVDT or any other dial gauges. But what you have to do is that you have to take the measurement at 15 independent locations. See, as you can see in this figure, see, this is the wheel load. Along the center, you have 5 locations, and 25 mm to the left and 25 mm to the right of your specimen, you have 5 locations. So, altogether there are 15 locations at which you have to measure the profile or the deformation. So, what you have to do is that initially you have to take the measurement, and then after a specified number of load cycles, say 100 cycles, you have to stop the machine and take the measurements and then close the chamber and then repeat the test. And at regular intervals, as I said, 100 after 100 you can go for 200, then 500, 1000 cycles of test. You can take these measurements at these 15 locations. So, this is a case of a large size device. Now, I will discuss about how the testing is done in a small size device in air. Okay. So, this is a chamber or an environmental chamber where the test is being conducted. Okay. As you can see here, this is the bottom plate in which the specimen is kept. You can see the wheel here. Okay. And then the wheel load is applied using a cantilever arm. So, you can see the cantilever arm here with the load applied at the end, so that the equivalent required wheel load will be applied through the wheel on the surface. Okay. Now, as I said, the wheel is a rubber hosed wheel of 200 mm diameter and the wheel path is of 50 mm width. Now, the test temperature, based on your requirement, you have to choose the test temperature. So as we are discussing about rutting is something which happens at a higher temperature. So normally we do the testing at 50 or 60 degrees Celsius, and when you have to condition the specimen to that test temperature. So if your thickness of the specimen is less than or 60 mm, you have to condition it in the environmental chamber for at least 4 hours. And if the thickness is more than 60 mm, you need to condition it for at least 6 hours, but to a maximum of 24 hours. If you continuously condition it at this test temperature for more than two days or so, what can happen is that the agent will creep in. The maximum time period duration of conditioning of the specimen is 24 hours, and if you are doing the test in water bath, it has to be conditioned for at least 1 hour. Okay, and as I said, the frequency of testing in a small size device is 26.5 cycles per minute, and one to and fro motion constitute one cycle. So you can say it is actually 53 passes per minute. Okay, and in the small size device, you use an LVDT to collect the data at different points in the specimen, and this is how the data is collected in a small size device. In the sample, along the central path of your wheel, you collect the deformation at 25 equally spaced locations. Okay. During the first 1 hour of testing, you will take the readings at 6 to 7 times in the first 1 hour, and thereafter at least one reading is taken for every 500 load cycles. You need not stop the test for collecting this data. The LVDT will automatically collect it during this test cycles without stopping the machine. Okay. Now, after taking this 25 deformations or the profile at 25 locations, average of these 25 values will be the mean profile of the specimen. Okay. Now, this test, the small size test, is conducted for 10,000 load cycles or till you see a rut depth of 20 mm. Okay. Now, as I said, for repeatability, at least 2 tests are to be conducted. Now, how do you process this data? Now, as I said, you have collected the rutting or the deformations from the original profile for a number of cycles, and you have tested it for at least 10,000 test cycles. So, the one attribute that you collect to find its rutting potential or rutting susceptibility is called the proportional rut depth. Okay, proportional rut depth is, or you can say it as a strain. So, this is calculated like this: Mij minus Moj by n into h, where Mij is the deformations that are collected from the jth location in the ith cycle. Suppose I am considering 100th cycle. So, as I said, I have 25 locations. So, from the jth location, what is the deformation that is collected, and subtract it from the initial measurement, so that you will get the rut. Okay. Then divided by n, that is the number of measurements that you have taken. So, that will give you the average profile, and divide it with the specimen thickness. So, that will give you the proportional rut depth. So, this is one way of estimating the rutting potential in terms of the proportional rut depth. And again, this value has to be computed for both the test specimens, and you can take the average. And the second aspect that you collect is the wheel tracking slope. So, this essentially is the slope of the rutting or the rut depth progression towards the end of your test cycles or towards the last 5,000 test cycles. So, suppose you have, this is your rutting progression, say this is rut depth versus the number of cycles. You measure the rut depth at the 5,000 cycle and then the 10,000 cycles, and the slope of this portion is denoted as the wheel tracking slope. So, it is d10,000 minus d5,000 by 5,000 into 100. Now, if in a case that the test is terminated before 10,000 load cycles, then you can calculate this slope again at the towards the end, or when you see that straight line portion of rutting happens. See, initially there is a curved portion and somewhere it reaches a straight line. So, in that straight line portion you can take the slope, but for that you need at least 2000 cycles to be completed in the test. Okay. Again, this also has to be reported as an average of 2 specimens. Now this is a sample plot of the rut depth versus number of passes. As you can see here, this is number of passes. So the test is continued for 30,000 passes, or you can say that this is 15,000 cycles. And you see the progression, and the final rut depth that has reached, that is this value, is 3.4 mm, and the tracking rate in millimeter per 1000 load cycles, you got it as 0.1175. Now this is one way in which you can post-process the data. There are other approaches by which you process the data and you set failure criteria for these materials. As per the AASHTO T324, which uses the Hamburg wheel tracker, the number of passes required to attain a 20 mm rut depth is taken as the criteria, or you compute what is the rut depth which is caused after a specified number of passes. Say for example, your test is for 10,000 cycle or 20,000 passes. What is the rut depth, the final rut depth that is reached at the 20,000 passes, that is taken as the criteria. Whereas in a study by Chen et al. In 2007, they have established a criteria called dynamic stability. So it is defined as what is the number of load passes that is required for a 1 mm rut depth. Okay. And there are failure criteria that are set by other researchers. Say for example, if you want to use that mixture in a light or medium traffic, you need a minimum dynamic stability of 800 cycles per millimeter. And if you want to use it in a heavy traffic, you need a stability of 3000 cycles per millimeter, and so on. One can arrive at such criteria provided you have sufficient amount of field data as well. Okay. Now there is, as per AASHTO TP63, using an asphalt pavement analyzer, it specifies that a rut depth at 8000 passes is taken as a criteria for comparing your mixes. Now this is a word of caution. When you use this kind of a test, as you know that this is a highly heterogeneous mixture and the repeatability is going to be very high, or what you can say that the scatter of data will be very large. So this is a study by Priyansh and Aravind, who have tried to see how much will be the variability when you use a test like a rut wheel testing. So you can see here that in the first figure, you are trying to find out what is the number of passes at to reach a particular rut depth. As you can see here, to reach a rut depth of this much, the variability is from here to here. So this is a such large variability of results when you use a wheel tracker test. The green portion shows the variability. Okay. Whereas in the second figure, you can see what is the rut depth which is corresponding to a number of passes. As you can see here, for this number of passes, the variability of rut depth is from here to here. So such wide variability one can expect when you do a wheel tracker test, and these variability can follow certain functions, like you can have a normal distribution, Weibull distribution, or a log normal distribution, and so on. So one has to be very cautious while using such kind of information to correlate it to the performance in the field. So let us discuss a little bit about what is the potential of this test and what are the issues associated. So one aspect is regarding the temperature of testing. You can do the testing at a higher temperature of say 50 or 60, wherein this the rutting or the possibility of rutting is more. So you can do a testing at that temperatures. But again, it can be done at a constant temperature alone for a particular test. And this is a test which will take a little amount of time. Say for example, 6 hours is required for 10,000 load cycles. And you can do the testing at different air void contents. What I mentioned in the as per the standards is at an air void content of 4%. Say one wants to test it at a higher air void content, as when the material or to simulate the material when it is laid and compacted, you can test it at say 7 or 8% air void content and see how the deformation happens. Or you can have a very low air void content and see how the shear deformation happens. So such possibilities are there to use in the rut wheel testing. Now what is important is that this, as I said, rutting is a very ductile phenomenon which go through a primary stage, a secondary stage and a tertiary stage. Now this evolution of rutting will be different for different materials and you should be able to capture this. But what we have observed in the sample data that I have shown you, that even you have extended it for a 15,000 cycles, you are not able to see a definite primary, secondary or tertiary kind of behavior. So this evolution over a period of time, it may not be visible in a simulative test like rut wheel testing, because the load and the conditions are simulated in such a way that you get a immediate result, or you say that you are not prolonging the test for sufficiently long, so that you may not be able to see all these kind of stages. And the major important aspect is the confinement condition. So as I mentioned in the case of ASTM standards, see, the confinement that is happening on the material in the field is highly varying. This will depend upon the load that is applied, at which point that you are trying to collect the information, and for a viscoelastic material, which bituminous mixture is, this confinement will depend upon the rate of loading as well. Okay, so all these aspects are not incorporated or simulated in your wheel tracker test because the material is placed in a very rigid mold. Okay, and the next aspect, as I already mentioned, is the 3-stage ductile behavior, which is not covered. And another aspect is the effect of rest period. Okay, as you know that after the application of one wheel axle or axle load, there is certain time period for the next wheel load application or the next axle load application. So during this rest period, there could be recovery of deformation that can happen, but that recovery is not considered in this kind of test, especially when it is done in a bidirectional way. As you have seen that in the accelerated loading facility, the wheel is actually loading in one direction, and in the second direction you have lifted up the wheel and the loading is not done in the other direction. Whereas in the case of a simulative test using dry wheel tracker or wheel tracker, the loading is done in the to and fro motion. So there is no rest period being given to the specimen. So these are some of the aspects that are to be considered while you use this as a indicative test for the rutting behavior of bituminous mixtures. And another aspect is that you need extensive field performance data that is necessary to correlate this laboratory investigation to the field data. But the main advantage of using a simulative test like this is that it is essentially a pass-fail test, and it can give you an indication of whether there is chances of any premature failure on this material due to various aspects such as a weak aggregate structure, inadequate binder stiffness or moisture damage. So such information can be obtained, and essentially it is a tool that can be used to rank different materials. We will be trying out different materials like polymer modified binders or unmodified binders. If you want to use get a comparison between the performance of these materials or to rank the different mixtures, this definitely can be used as a effective technique. Now let me discuss a little bit about how this test has to be correlated to your mix design procedure. Okay. Now we in India follow the Marshall method of mix design. As you all know, this is the steps for Marshall method of mix design. The first step is the aggregate selection, and then comes the binder selection, and you prepare the sample based on the compactive effort that is there in the field, or based on such correlations. You compact the specimen and prepare the specimen, and you do its volumetric analysis. You compute parameters such as density, voids in mineral aggregates, voids fills bitumen, and so on, and then you determine two aspects. One is the stability and flow of the material using a Marshall stability test. Okay. And finally, the optimum binder content is chosen based on a design air voids, say for example 4%, and then you check for the stability and flow whether it meets the required criteria. Now what is there in this whole aspect is that you have your volumetrics part and then you have a stability and flow part, okay. But these two aspects are not correlated to the rutting behavior, or it is not a strength parameter as such, okay. So, no strength parameter is being used directly in this Marshall method of mixed design, whereas one needs to correlate this kind of a testing wherein rutting phenomena is simulated. That has to come into the mixed design, so that before you choose your binder content or the mix as such, okay. So, you have seen many developments in different countries, and this is a mixed design strategy that is adopted by Ostrode, or it is the Australian method of mixed design. As you can see that it is divided into 3 levels, okay. So, I am not going into the details of this test, but I will just introduce what is the 3 levels is. One is level 1, wherein you look into the volumetrics similar to your Marshall method. So, you have the selection of materials, then you compact the materials at different binder contents, and you evaluate its voids, density, voids in mineral aggregates, etc., and you arrive at the design bitumen content, okay. So, your bitumen content for that particular mix is determined based on the volumetrics. Then you go to the level 2, wherein various aspects of the mixture such as durability, then the modulus of the material, then creep and creep compliance, fatigue resistance, and moisture sensitivity. So, all these aspects of the mixture has to be considered in the level 2 of your mixture design, and once approved through all these aspects only, it goes to the 3rd level, okay. And in the 3rd level, the material is again prepared with, or the mixture is again cast with the designed binder content, and then you do the wheel tracker test and the wheel tracking rate is reported. If this does not satisfy the requirement as per the standards, you have to redo your mix design. So, this is a whole procedure wherein which you consider the volumetrics, and in addition to the volumetrics, the various durability parameters, the strength parameters is also taken into account for designing the mixture. Okay. So, with that I conclude this lecture. We will continue with the other bituminous mixture testing or the performance related testing like flow time and flow number test in the upcoming lecture. Thank you.